Morning, everyone, and welcome to this webinar session. It is our great pleasure today to have Jessica Santos speaking and presenting her work. I will tell you a few words on Jessica. Jessica Santos is a PhD student at the University of Aveiro in Portugal in the Material and Ceramic Engineering Department and also in the Center for Food Technology and Packaging of ZOO School of Life Science and Facility Management in Switzerland. Jessica obtained her master's degree in food biotechnology and a bachelor's degree in biotechnology from the University of Aveiro. Then she was a research fellow in the Plastic Coolite project that aimed to develop lightweight fillers for plastic formulation, from egg byproduct in collaboration with industry partners. She also had the opportunity to participate in various international scholarship exchange programs, such as the PROM program, the Circulability STSM Cost Action, and the Netpore STSM Cost Action. Her interests include the exploration and characterization of biomolecules from agri-food industry byproducts and their further application for the development of porous particle and bioplastic composites for food packaging application. Jessica already has a nice scientific achievement with 4 publications in international review and journals, 12 communication in international conferences, 13 posters also in national and international conferences, already 4 international internships, and 1 participation as a chair in a conference session. So Jessica, please, you're welcome to start.
Thank you. I will share my presentation. I am Jessica. I am a PhD student, almost in the end. And today I am going to talk my work related with porous ethylene scavengers derived from agri-food byproducts for active food packaging. Ethylene is a natural compound, a phytohormone, that plays a key role in the ripening of fruit and vegetables. However, the exposure to high levels of ethylene can contribute to significant food loss and waste. So, to address this problem, research has been focused on developing porous materials with capacity to absorb ethylene. And by reducing the levels of this phytohormone, we can extend the shelf life of fruit and vegetables and promote their freshness. On other hand, agri-food byproducts, often discarded, offer an opportunity since they are a source of biomolecules that can be used for materials development, namely porous materials. So, the main goal of my work, my PhD work, was to explore the repurposing of 2 specific agri-food byproducts, namely pine nut skin derived from the dried food industry and brewery spent grain derived from brewing industry to develop ethylene scavenging particles. To achieve these main goals, I explored 2 different approaches. In the first approach, I used pine nut skin as a source of cellulose and lignin to develop aerogel particles that are able to absorb volatile compounds. And in the second approach, I used a brewery spent grain as a source of carbon to develop activated carbons to enhance the capture of this phytohormone. Within the first approach uh, um, to develop aerogel microparticles, initially I started my work by fractionate pinette skin to obtain residues rich in cellulose and lignin with different molecular weights in high molecular weights and low molecular weights. And I use it as reference commercial microcrystalline cellulose. And then I used all of these residues to obtain aerogel particles by emulsion coagulation. Briefly, in this technique, I firstly started by preparing suspensions containing the residues, cellulose-rich residues, in alkaline solutions, and then I emulsified these suspensions in paraffin. In parallel, I prepared a second emulsion containing in the droplets and cellulose non-solvent. In this case, I used acetic acid. And by mixing these two solutions, I promoted the coagulation of cellulose within the droplets and I formed microgels. Then these microgels were submitted to solvent exchange to ethanol, and they were dried by under supercritical conditions to obtain aerogel particles. And during the formation of these particles, I also tested the inclusion of zinc oxide in the alkaline solutions as to promote the cellulose dissolution and swelling within each droplet. And as it's important to understand the swelling properties of cellulose, it's important to study the rheological viscoelastic properties of uh, solutions containing the initial residues derived from pinette skin. And for cellulose in alkaline mediums, usually the typical viscoelastic behavior is represented like this, in which we can see that the viscous models initially is superior to elastic models until the curves can cross, and in this point it is called as gelation point, where there is a transition between the liquid-like states to gel-like states, in which there is a formation of polymer network. And we can see this typical behavior uh, in this sample, the cellulose of low molecular weight, in which we achieved a gelation point at 7.5 hours. And the presence of zinc oxide did not impact the gelation point of this sample. We can see also this typical behavior um, from the particles obtained from microcrystalline cellulose in the presence of zinc oxide, and the gelation point was achieved after 4 hours. Interesting that in other samples we can see that the elastic models is immediately superior to viscous models immediately after the initial steering, which means that these samples are immediately at the solid state or gel state, which demonstrates the swelling capacity of all of these samples inside each droplet of the emulsion. After the development of aerogel particles, in terms of size, we can see that the aerogel particles obtained from the residues with high molecular weight have a broad size distribution when compared with the particles obtained from low molecular weight, but these ones are still larger than the ones obtained from commercial microcrystalline cellulose. And it is interesting that the presence of zinc oxide seems to slightly decrease the average size of the particles. In terms of morphology, we can see that the residues with high molecular weight generated particles with irregular shape, as you can see in here and in here, while the particles obtained from low molecular weight, from cellulose and cellulose lignin residues, have spherical shape and are more homogeneous than the other ones. And the presence of zinc oxide seems to enhance the visible macroporosity, as you can see in here and in here, which can be related with the rule of zinc oxide on cellulose dissolution. In terms of polymorphism of cellulose, we can see by the first curve of all of these graphs that all finite residues present type 1 cellulose, which is related with the parallel orientation of cellulose chains in crystalline domains of this polymer. But in aerogel particles prepared without zinc oxide, we can see that the presence of both polymorphisms, like type 1 and type 2, which means that there was a partial conversion of cellulose of type 1 to type 2. Um, and it was probably related with the use of alkaline solutions during the aerogel preparation. But it is interesting that when I use a zinc oxide to promote the cellulose dissolution during the preparation of aerogels. Um, all of the aerogel particles obtained in the end um, were at type 2, as you can see by these curves, which means that zinc oxide promoted the total conversion of type 1 cellulose to type 2 cellulose, and type 2 means that cellulose is uh, is in the anti-parallel form. The cellulose chains orientation is in the anti-parallel form, which means, and this means that zinc oxide has effectively a role in dissolution and swelling properties of this polymer. In terms of porosity, we can see by nitrogen isotherms that all the samples presented type 4, which means that the aerosol particles are mesoporous materials. And in this table, we can see that the presence of lignin in the particles with high molecular weights reduced the surface area or size. And it also happens in the particles with low molecular weights. The presence of lignin decreases the surface area and pore size. And in turn, the presence of zinc oxide increases the surface area when compared with the corresponding samples without zinc oxide. And this also it again reinforced the idea that zinc oxide has effectively a role in this, promoting the swelling properties of cellulose inside each droplet of emulsion. In terms of ethylene absorption, which was my main goal in this PhD, we can see by these curves that all samples presented higher capacity to absorb ethylene than the aerosol particles obtained from commercial microcrystalline cellulose, except this one. And it can be seen that mainly for high pressures, we can see that the presence of lignin promoted the ethylene absorption on these particles. And it can be explained or can be related with possible PP interactions between ethylene and polyphenol extraction of lignin. Um, And since it was the first time that aerogel particles were tested as gas absorbers, I compared the most effective particles with traditional porous particle, traditional adsorbents like commercial activated carbon and spiolates, and it can be seen that my particles had less activity when compared with traditional ones. However, their activity is close to HBI 15, which is a benchmark material. In another part of my work, uh, for developing active carbon, I used spent Bowery grain as raw material, and I obtained these activated carbons by pyrolysis at 1800 Celsius degrees using different activated agents, namely sodium hydroxide, potassium hydroxide, and potassium carbonate. And I studied the impact of these activated agents on physicochemical, morphological, and ethylene scavenging activities. But I also wanted to test the presence of different chemical groups, surface chemical groups, on gas absorbing properties. So I submitted this activated carbon to functionalization to obtain oxygen, nitrogen, and sulfur groups on the surface of these carbons. And in terms of chemical properties by FTIR, we can see that the activated carbon obtained with sodium hydroxide presented a very similar spectrum when compared with a commercial activated carbon, lacking oxygen groups as the other ones, meaning that this specific activated carbon presented a very polyaromatic and graphitic structure when compared with the other ones. Uh, and we can see that the functionalized activated carbons um, had very similar spectra when compared with the initial one, which means that by FTIR it was not possible to see the chemical differences. It was not detected the functionalization by this methodology. In terms of the title is wrong, sorry. In here, I am presenting the results related with porosity, and these are the isotherms obtained from the activated carbons produced with different activated agents and the activated carbons with different surface functionalizations. And the isotherms are all type 1, which means that all materials are microporous materials, with some character of type 2 isotherm, which means that they have also fractions of macroporosity. And in terms of surface area, we can see that the activated carbon obtained with potassium carbonate was the one with highest surface area and lowest pore size. even when compared with the commercial one. And the functionalization of this activated carbon maintained or slightly decreased its surface area, but it didn't impact strongly the size of pore. In terms of morphology, all activated carbons consisted of microparticles or aggregates with very heterogeneity, and it is also possible to see macroporosity fractions in almost all of these carbons. In terms of ethylene, we can see in this graph the isotherms of adsorption of different carbons obtained with different activated agents. And we can see that the one that was most promising was the one obtained with potassium carbonate, followed by the one obtained with sodium hydroxide, potassium hydroxide, and the commercial one. Um, and we can see a huge difference between the most effective when compared with the commercial one. In this second graph, we can see that the um, functionalization did not impact positively the ethylene adsorption, probably related with decrease of surface area when compared with the initial one. But uh, looking for these results, I saw that there is a huge impact of surface area on absorbing properties. But I wanted to understand the affinity of ethylene uh, when in terms of chemical surface properties. So I tried to understand the ethylene absorption per unit of surface area to understand the affinity of ethylene with different surfaces of the carbons. And we can see that the carbon obtained with sodium hydroxide presented a remarkable affinity to ethylene when compared with the other ones per unit of area, which means that the polyaromatic structure of this specific activated carbon promoted the ethylene absorption. And probably it happened uh, one more time by the possible PP interactions between the polyaromatic structure of this carbon with ethylene. And based on these results regarding with ethylene absorption capacity of the materials, and based on the reported ethylene production levels of different fruits and vegetables, I calculated required amount of material to preserve 1 ton of packaged food, in this case, fruit or vegetables. And we can see that the activated carbon produced with potassium carbonate, which was the one with highest ethylene absorption capacity per gram of material, this specific activated carbon needed almost 6 times lower amount when compared with the carbon with the commercial available activated carbon. And this indicates a potential benefits in terms of economic and environmental benefits. So, to conclude, uh, I would like to put again the question, can finite skin and brewery spent grain residues be used as raw materials for developing ethylene adsorbents? The answer for me is yes. During this presentation, I showed that finite skin uh, are rich in cellulose and lignin, and the residues derived from these byproducts are able to gelate in sodium hydroxide, zinc oxide water systems, and this swelling in and emulsion can generate aerosol particles with a mesoporosity. Sorry, I will have to charge my computer. So these residues can generate mesoporous particles with this range of surface areas, and they are able to absorb ethylene, although it is necessary still some improvements to achieve the traditional solvents for this purpose. I also obtained activated carbons from brewery spent grain, which are mesoporous materials with high surface areas and with that's demonstrated to be effective for ethylene absorption and require almost 6 times lower amounts to have the same effects as a commercial activated carbon. To finish, I would like to thank especially my supervisors, Dr. Paulo Ferreira, Dr. Idalina Gonçalves, and Professor Del. I would like also to thank the departments where I developed my work, namely University of Aveiro, University of Coimbra, University of Zurich, and the Technic of Lisboa. The FCT for my grant, and especially thanks for Netpore cost action. Thank you.
Thank you very much, Jessica, for this very interesting and very nice presentation. So now we have time for questions. Please, you can raise your hand using this little icon or just start speaking if you have questions for Jessica here. Don't hesitate. It's a very interesting topic on sustainable materials preparation. And so I may start if no one has a question at the moment. I have a couple of questions. So the carbon material is a nanoparticles or micron-sized particles?
Microparticles.
Macroparticles. And the question is, do you have a nice comparison between the different surface you have from the aerogel microparticles or carbon microparticles? But if you compare those two type of material, is there one that has better property to absorb the ethylene?
Yes, the activated carbons are especially better than aerogel particles because they are microporous, and ethylene is especially absorbed when we have a small pore size to block this phytormone. But the idea was to promote sustainability, and aerogels are more biodegradable when compared with carbons. That's why I tried to develop this kind of materials. But yes, the activated carbons are really uh, as have really higher performance when compared with the aerogel particles. Yes.
Right. Yeah, thank you. And the aerogel material has have a very nice advantages that you mentioned. So what would you think about as a use for these materials besides ethylene absorption? What would they be good for?
They can be good for encapsulation of compounds. They can be used to absorb water, for example. They're especially hydrophobic, so I believe it will be a good purpose for them. But they have been applied for other kind of fields in biomedical and food packaging. Yes.
Very nice. And
Maybe in the future I
one
can
more.
explore my answer.
Yeah, sorry. Okay. And one more question, maybe a more general question. Uh, do you have an idea of the yield of generation of those material in terms of quantity? can you extract, can you generate a lot of material from this process, or it's a reduced amount that you can get?
In terms of aerogel, I believe that all the residues that are put in the solution can be present in the final aerogel because there is no loss, almost no loss. Only maybe some soluble compounds that can be released to the water, but they are not especially totally soluble, so cellulose and lignin. So, but in terms of activated carbons, I believe that the yield is lower than 20% when compared with the dry mass of byproduct, the initial byproduct.
Okay, thank you. Thanks a lot.
Thank
Do
you.
you all do you have any question in the audience for Jessica? No? So if not, then we can thank Jessica and maybe applaud. Thank you very much, Jessica, for your nice presentation. Thank you all for your participation at this webinar today, and we hope to see you in a month for the next session of the Netpore webinars. Thank you all and have a great day. Thanks a lot, Jessica. Wish you a very good day.
It was a really pleasure for me. Thank you.
Yeah, thank you.
Thank you.
Thank you, Eleonora. Thank